Hi. Tonight what I want to talk about is alcohol, how to obtain it and how to concentrate it. And I also want to revisit something that I discussed earlier on how to sterilize or disinfect masks. Alcohol is the workhorse of most of the disinfectant solutions that you're going to find out there, and we've covered how to modify it and enhance it by using either benzalkonium chloride or citric acid. But the alcohols, because they're in such demand, are difficult to obtain nowadays. And so one of the things that we have to first eliminate is methanol as a potential option. You can get this at auto supply stores for dehydrating gasoline, and it is not a good disinfectant, so we don't want to even look at methanol. What we do want to do is look at either isopropyl or ethyl alcohol, which are almost equal in their disinfectant capabilities. The problem is that the optimal concentration for the alcohols is around 70%. The point being that if you go to a lower concentration like 50%, it's not very toxic to the microbes. And if you go to a higher concentration like 90%, it tends to sear the outer capsule and not penetrate quite as deeply. It's not actually as lethal as the 70% concentration. It's also becoming very difficult to obtain either of these concentrations, although this is still pretty easily available. If you go to ethyl alcohol, you're basically going to booze. And if you can obtain, say, Everclear, which is a 75% solution of ethyl alcohol and water, great. But the problem is this too is becoming difficult to obtain, and so you may be limited to, say, a high-proof vodka, and at 50%, it's still not high enough. So what I'm going to discuss is techniques that you can use to increase the concentration of the alcohol. Now, if you've seen some of our other videos, I go into some detail not only about how to ferment and make your own alcohol from scratch, but I also have a video that describes the process of distillation itself. And it's an interesting process. It's kind of fun, and if you take a look at that, I'll go through not only the principles and the mechanisms, but the components of the apparatus. And if you like that, it might be something that you might want to get into because, like I said, it's kind of interesting. However, it does involve an investment, and unless you want to do what I do when my wife, asks me to do some sort of a remodeling project, and I use that as an excuse to buy hundreds of dollars worth of power tools, you may not be interested in the process. You might be just interested in the end result. So you may not want to invest in this, even though it is an interesting process. You might just want to do something that's a little less expensive and a little bit easier. Now, one of the advantages of distillation over any of the other techniques I'm going to show you is that it not only can draw the water out of the alcohol and concentrate it, but it can also separate the individual alcohols from each other, methanol from ethanol from isopropyl. None of these other techniques do that. They simply draw the water out, but they're also a lot less expensive in terms of the initial investment. One technique that you can use is what's called freeze crystallization or freeze concentrating. And it's often done to, say, take hard cider or beer or wine and enhance the amount of alcohol by placing this low percentage concentration alcohol and water into a vessel or a flask inside of a freezer. And as the surfaces of the container become cold, you get these needle-like crystals of nearly pure water forming within the solution. And therefore, what's left still liquid is higher and higher in its alcohol concentration. The problem with that is it only works to relatively low concentrating factors. You can't get high concentrations of alcohol to concentrate that way. First of all, you probably don't have the ability to refrigerate to a temperature that's going to freeze these. You'd either need to use dry ice or liquid nitrogen. And when you do that, you tend to get sort of a slurry, kind of a mush. You don't get the fine crystals that you can then separate out in order to increase the concentration. So it's not practical for this application. One technique that is available is what's called salt concentrating. Isopropyl and ethyl alcohol are completely soluble within water. And if you sit a bottle of, say, 50-50 water and alcohol on a table, it can sit there for years, and you don't get a separation of the lighter alcohol and the heavier water because there's an affinity for the alcohol and the water. The molecules actually have enough of an affinity for each other that affinity overcomes the differential densities of the liquid, and they remain in solution forever. However, if you introduce an ionic compound like table salt, sodium chloride, the water, which is very polar, is very attracted to very highly polarized or ionic species like salt. And so when you put the salt into a mixture of water and isopropyl, the salt will attract the water out of the isopropyl, leaving behind a supernatant that has less water in it and a lower, denser layer which contains saturated salt water. So what I'm going to do is show you how this works. It's kind of neat. I'm going to take this jar, ball jar, and I'm going to fill it with 300 milliliters of 50% isopropyl and water. And then I'm going to blend into this a 6:1 by volume, so 300 cc's and 50 cc's of simple salt. This is kosher salt. You can use any kind of salt you want. And the quantity is not that critical. As long as you use enough salt that not all of it dissolves, you've essentially created a supersaturated solution. 6:1 is a good ratio where you'll still have a little bit at the bottom. Anything in addition to that is simply going to be left or wasted. But anything less than that, in other words, if you dissolve it all, you probably haven't maximized the reaction. Now this takes a little bit of time to work. I'm going to let this sit for a little while. But I'm going to show you an interesting distinction between isopropyl and ethanol. If I take 50%, same concentration, of ethyl alcohol in water, and I add this into the jar to 300 milliliters. And then I'm going to mix in the same quantity of salt, in other words, 6:1 or 50 cc's of salt, into this. And then we're going to mix this up and let it sit for a few minutes. Now, I don't want to shake this too much. We'll just let this sit here like that. Now, I'm going to show you how we measure the density of the alcohols. This cylinder here, I'm going to fill it with the 50% isopropyl and water. And then I'm going to use a hydrometer to measure the density. Now, this will float at different heights based on the density of the liquid it's in. And then you'll see at the top the measurement of the amount or the percentage of the alcohol in the water. It's calibrated for that purpose. So we'll let it just sit down there for a second, stop spinning. And we can see right here that this is running at about 56% alcohol. So it's a little bit, they were a little generous in the concentration. And if you take a look, I don't know if I'm going to need to use the flashlight, but you will start to see in the IPA or isopropyl alcohol, right about here, right about at this 4-ounce marker. I'll see if the light helps us at all. It may or it may not.
I can see it.
You can? If I shake this a little bit, you can also see that level kind of wiggling or moving back and forth. This below here is the water and salt. This up here is a concentrated solution of the isopropyl and isopropyl alcohol with a little bit of remnant water in it. However, if you look at this, this is the ethanol. You don't get such a division. Now, the reason this occurs is that isopropyl alcohol is a less polar molecule. The water is the most polar of solvents. It is very asymmetrical in its electronic charge, and as you get longer and longer hydrocarbons, the liquids become less polar, more oily, less able to dissolve in water. Isopropyl has a rather weak affinity for the water. Ethyl, which is a smaller hydrocarbon, has greater affinity for the water. So even though the salt will tend to pull hard enough to get the isopropyl to separate from the water, the ethanol is not. So you can't use this technique in order to get the concentrating effect that you want with ethyl alcohol. You have to use a different technique. Now, just to demonstrate, in fact, that this worked, what I'm going to do is I'm going to take this carefully. I'm going to try to remove the top without shaking this too much. And over time, this will continue to improve. If I give this another half hour or so, I'm going to actually gain a little bit more purification, but this is going to be enough for this purpose. You remember that I demonstrated with this cylinder and with the hydrometer that I had about a 56 or so % concentration. If what I do now is I take a syringe, now you can use a medical Toomey syringe, you can use a simple 50 cc syringe. If you're careful, you can even use a basting syringe. And what you want to do is you want to pull the liquid off the top without pulling the concentrated liquid at the bottom out. So as I draw this up, I want to do it relatively slowly and right from the surface. And as I do so, I'm going to primarily be pulling the alcohol off the top and leaving the water behind. The slower, the better. And again, the longer you wait, the better this will work. You could leave this overnight, you could leave this for days if you wanted to, and you just get a little better result. Let's see if that's enough. Now, I probably should wait a little bit longer. Obviously, I was being pretty quick. But you can see that it already is concentrating a little bit more. We're at about 62%. And again, if I wait about another half hour, this will drop to about 65. And if I wait overnight, I will get it to 70. We can't get this to work with the ethanol. As I said, it doesn't form any kind of a division. And so in order to concentrate ethanol, we have to use a different technique. And that involves using what's called a molecular sieve. Now, this is a very interesting material. What they do when they form this is they take aluminum silicate and sodium silicate and they mix it with water and form sort of a paste, and then they extrude this through what looks like a pasta maker into these long spaghettis, and then they slice them up into these little prills. They heat it to about 400, 450 degrees centigrade, dry it out, and then the drying process causes small defects, cracks, and pores to form within the material. As a result, the surface area of this macroscopically might be, say, half a square meter. But the surface area, if you include all those little pores and cracks that form, could be as much as 1,000 square meters. Now, surfaces all have a stickiness to them. When you have a bulk material, the atoms that are inside of the material have electrons that are attracted to their nuclei, but they also are very slightly attracted to the nuclei that surround the individual atoms. And so there's a slight attraction in all directions, isotropically, around each one of the atoms. But when you come to a surface, the electrons are pulled slightly to their neighbors inside, but the outside surface is somewhat needy, and as a consequence, there's a bit of an attraction to any other surface that may get near it. All surfaces tend to attract each other, and this force of attraction is called a van der Waals force. That force is useful because of the fact that on the nanoscale, it's powerful, and it can actually pull molecules against a surface. So when we form a molecular sieve, the outer surface attracts molecules like alcohol and water, but the inner surface, because it has very small cracks in it, will only attract molecules that can get inside of those pores. When this is initially formed, it has grooves and pores that are on the order of about 4 or 5 angstroms across. But if they do what's called cation exchange, they replace some of the sodium with potassium, which is a larger atom, some of those spaces narrow up a little bit. And so instead of a 4 or 5 angstrom opening, it'll have a 3 angstrom opening. That's why this is called a 3A, 3 angstrom or 3 picometer molecular sieve. Water is one of the smallest molecules out there and has a diameter of about 2.5 to 2.8 angstroms. It can get into the pores. But the ethanol and the isopropyl is bigger, 3.5 to 4 angstroms. It can't. So when the surfaces attract the liquids, the outer surface, the macroscopic surface, will be saturated by just a fraction of a milliliter of the alcohol. But the inner surface can hold a great deal of alcohol as an adsorbed material. And so as the alcohol is left behind and the water gets into the pores, the alcohol concentration outside will increase versus the original solution. And you can concentrate the alcohol by adsorbing preferentially the water. Now, what's interesting about this is that the process itself increases entropy. And when you increase entropy, create more randomness, you mix things, they tend to heat. This process is exothermic. So if I take the 50% ethanol and I add this to this desiccant in a 1-to-1 by volume ratio. So if I have, say, 400 cc's of the molecular sieve, I want to add 400 cc's of the 50-50 ethanol and water. When I put that in here, you're going to see an interesting thing happen to the temperature. It gets very, very warm. I'm going to turn on my little thermal monitor here, put my probe in here. You can see it's not even 20 degrees. And when I pour this in here, it becomes so hot, it actually steams a little bit. And you'll see that the temperature very quickly rises. And that is an interesting or useful endpoint, because as the temperature goes up, obviously the adsorption process is continuing. After a couple of hours, all of the water has been adsorbed. This cools with equilibrium with the environment, and this gets back to room temperature. You're essentially done. 3 or 4 hours is enough. You can leave it longer, but once it's cool, the process is done. Let me show you how effective this is. I'm going to take this and put it under a little filter, a little coffee filter inside here, to get rid of some of the fines. The material, if you abrade it or move it around, shake it around, is relatively soft, and you can get some of the material to sort of abrade off, and you'll get a little bit of a foggy or a dustiness to it. Over time, this will actually settle out if you wait overnight, and the fogginess or the cloudiness in the mixture will disappear, and it will become crystal clear. Another trick you can use is to place this desiccant in what's called a sieve, or like a flour sieve or a gold panner's sieve, that will allow you to take the entire disc-shaped container and place it inside of a large pot. Pour your alcohol in there, let it do its thing. When you're done, pull the alcohol or pull the sieve out, and then let the material dry overnight to remove any of the organics that may be in it. And then once the organics are done, you can put the whole sieve into an oven at 260 degrees centigrade or 500 degrees Fahrenheit for 2 hours. After that point, you've driven off all that adsorbed water, and you can reuse this over and over and over. If you don't want to get something like the sieve in a pot, you can do it the way I did and simply put it into an aluminum pan and cook it as I described, making sure that you evaporate all of the solvent that may be on the outside, because it's obviously flammable. But once this appears to be dry, the rest of it will be water. Now this was 50-50 alcohol and water. Pretty good. Now this will work with isopropyl. This will also work with even low concentrations of alcohol like wines and beers and apple cider. But again, as I said, any method of concentrating ethanol is considered to be a regulated business. So as long as your governments remain intact and you don't want to get into trouble with local authorities, this is just for educational purposes. Now, while that's continuing to drain in here, what I'd like to do is I want to get onto the idea of making a correction. Last video, I had described a technique for sterilizing or decontaminating masks. And I love the comments, because when you're putting out videos that are seen by hundreds of thousands or millions of people, inevitably there will be people out there that see the videos that know more about any topic that I talk about than I do. There's going to be experts in every field. And we got a lot of comments about my recommendation of the cleaning, including a reference or a link to an article that was published by some researchers at the material science department at Stanford. Almost the same time that I had filmed that video, they put out this paper. And what they proved, what they demonstrated, is that the alcohol technique tends to inhibit or defunctionalize part of the operation of these masks. What happens is that a typical mask, which has polypropylene fibers in it, is made more efficient without making it super thick by putting an inorganic material on here which has a very strong surface charge. In other words, a very strong van der Waals force, and will attract particles like viruses into the mask without making it super thick. It makes it an N95 mask. When you wash this off with either hydrogen peroxide liquid or detergent or ethanol, what happens is you will neutralize some of that electrostatic effect. Now, the minerals are not soluble in the water or the alcohol, but in fact it may mechanically remove some of them, or it may actually bond to some of them, reducing some of their electrostatic capabilities. So you decrease the functionality of the mask, even though it apparently doesn't change it. They came up, though, with a better method, and it turns out that it's easier because it doesn't use any consumables. And what it involves is heating the mask in dry air to 75 degrees centigrade for 30 minutes. That's it. You can achieve that kind of heating in a regular home oven. I wouldn't recommend using that because a typical home oven is not very stable in its temperature. Their performance was rated on the fact that you get it to 75 and you keep it at 75 for half an hour. A normal home oven does this sort of up and down around the mean, when, especially a gas oven. It heats, it cools, it doesn't maintain a very fixed temperature. And secondly, you might not want to take a skanky mask and put it into the same oven where you're cooking your food. In a previous video that we had done, I described very quickly, touched on, this small oven that you can make yourself for about $35 out of very easily available materials that you use for curing epoxies and curing paints. And I want to go into a little bit more detail about how you construct this, because it's actually a very convenient device for cleaning the masks. This fiber material is a resin-bonded fiberglass that on its non-metallized surface is good up to about 240 degrees, 220 degrees centigrade, so plenty hot. It's also lightweight, it's stiff, it's easily cut with a box cutter, and you can form it into a nice box shape of whatever dimension that you like for maybe a half hour's worth of work and about $15, using some aluminized tape to adhere it so that it's not going to peel away due to humidity. This stuff is very good to resist humidity and temperature changes. And because this is normally designed to work with heating and cooling systems to insulate ducts from outside temperatures, retain the heat inside of ducting in a heating system, it's made for this purpose. Once you form your box and you have the dimensions of the bottom, you can then simply cut a square that is equal to the size of the bottom. And then, without needing any kind of fancy brackets or any kind of hinges, you simply drop the container over the bottom and you have a sealed insulated box. It's very easy to build. In addition, when you're done with this or you want to store this, it's easy to put this on a shelf and simply slip this inside and you put it on a shelf super easy. The heating is also very easy. If you take some simple incandescent light bulbs, in Europe I guess these are difficult to obtain, but you can get them specialty for, say, the lights inside of an oven. But a typical light bulb is perfectly fine with the temperature, and an incandescent light bulb rated at 100 watts produces 100 watts of heat. Whether it's making it light or infrared, it's 100 watts is 100 watts. If you wire these in parallel to each other, each one is drawing 120 volts as it does in the United States. And if you use silicone-based wire. This is a very nice wire because it's a lot more flexible than the typical electrical wiring that you use in your house. And this is good to 75 degrees centigrade. This is up to 150 degrees centigrade. It's relatively inexpensive. It's easier to work with and good for high temperatures. And if you get the fixtures for the lights made out of ceramic instead of plastic, a ceramic material, this also is good for high temperature. If on the bottom surface you're going to put these down on the aluminized surface, you're going to want to cut a small circle and peel the material off so you don't have a grounding that can occur across the electrical contacts. I discovered that the hard way. And once you've attached these, or placed these on here, then to attach them, you simply take a couple of fender washers and some long screws to penetrate here into some small nuts. And if you effectively tighten these down enough, you can cause them to become flush with the surface so that you don't need any legs and it won't scratch a tabletop. It's really easy. And then finally, to control the temperature, on eBay or on Amazon, you can obtain these thermostatically controlled relays that you can adjust the temperature in 1 degree increments. These can be obtained for maybe about $12, $14 up to about $30. They'll work either on 120 or 220 volt, and they have a little thermal probe so that when you build your box and you put the top down like this, you can then either drill a hole in the top or you can drill a hole in the side and simply insert the probe down to about the height where you're going to be doing your heating. Because the box is so well insulated and the heat source is relatively low grade, the differentials within the box are so small you don't need to use any kind of a cooling fan or distribution fan. It's not necessary. The differentials are very small, so it keeps it very simple. And when you're done with this, you can use this obviously for epoxy work or curing work, or you can simply take the box cutter and slice this up again and throw it away. It's inexpensive, it's very easy, it's very convenient to use. So I'd recommend doing this instead of the alcohol technique. I appreciate the advice from people about using these different sorts of techniques. And what's interesting is when I had criticized the WHO and the CDC about their recommendations for the masks and went through the principles and gave some examples as to why it was an incorrect recommendation that people who do not have an infection should not be wearing the masks, it turns out that they've turned around in their recommendations and have now agreed with us. So anybody who thought about it, thought through the process, would have come to the same conclusion, but a few weeks earlier than they did. Now, that brings up another point, and I want to sort of conclude the video with this. And that is the safety measures that I'm showing you here are real-time safety measures, how we protect ourselves, kind of like getting a fire alarm in a house. But one of the things that we do have to consider is the source of this virus is going to be something that we're going to have to at some point get a better handle on, because it doesn't make a lot of sense to get a fire alarm but not take care of the oily rags or the bad wiring in your house. If this can reoccur because we don't know how it occurred, we're going to have to deal with this again and again and again. And the source and the agencies that have been dealing with this obviously have a vested interest in what's revealed, because potentially with the deaths involved in this disease as well as the huge global impact, there's going to be a lot of cover your rear end about what caused this virus. So I don't want to touch any more closely on this rather delicate component of this whole issue. I want to suggest that you continue to use your head. Don't panic, because as I said before, I really don't think that this is going to turn out to be worse than we fear. I think it's actually going to turn out to be less serious than we fear. But again, being more prepared is better than being less prepared. So don't panic. Please, don't worry. Just use your head, stay safe, subscribe, give us a thumbs up, give us a comment, and I'll try to answer as many of the questions as I get. I'm sure there'll be a lot. You have a wonderful night, and take care.